Okay. First of all, I want to thank PyData for inviting me to speaking on this forum. It is not my first time. I think it is my second or third time I'm speaking here. And today we are going to talk about state space models, or SSMs, and deep learning. And we discuss if is there a new revolution at our doorstep, which is related to these SSMs and deep learning. And the main lecture objective will be to explain some math behind these SSMs. The math behind the SSMs may seem a bit complicated, but I'll try to convey it in the form which is more or less understandable. I can't do it without any math, but I try to simplify this math as far as I can, but Okay, and the outline of this talk, we are going to talk about transformers and RNN and the pros and cons, and then they're talking about the most important thing of this lecture, which is importance of memory representation for sequence modeling. When we will talk a bit about the first paper which introduced this concept of SSM. There are quite few people who know this paper, and the author of this paper definitely didn't get enough credit for that. And then we'll be talking about some cons, some shortcomings of these SSMs, and we will talk about selective SSMs, which kind of trying to solve this problem. And then we'll discuss shortly, if time remains, some domains we can use SSM to solve problems. Okay. My name is Mike Erlihson. I'm head of AI in a cyber startup. We are currently at a stealth mode. We are doing DLP. Unfortunately, I can't tell you more than that. I'm pretty active on the social media. I have some followers on LinkedIn. I have 2 Telegram channels with more than 2,000 followers, and also I have some. I like writing deep learning paper reviews. I wrote about 370 reviews. And also I have 2 podcasts, one in Hebrew and one in English, Data Science Decoded and Explainable. So you are invited to follow me in any of these platforms. Okay, so let's start talking about transformers. Everybody here knows what is transformers, and we are using transformers for many tasks. The transformers feature our LLMs, which we love, and we are using it practically for any task. And I think all of you know that the attention mechanism is a main mechanism which enables this good work of the transformers. But apparently it has some shortcomings, and we are going to tackle these shortcomings with the SSMs. And what are these shortcomings? First of all, let's discuss no shortcomings. Let's discuss some advantages of the transformers. In the transformers, when you predict next token is a subword. It can be some patch representation in an image or in a video, and subword in a natural language. When we predict a token, we tend explicitly all the tokens which precede this current token we are going to predict. And this it is very good because it enables a parallel training, but it has a very serious issue. And this issue is an inability of the transformer to work with very long scales. As far as I can see, if every token needs to attend explicitly, which is very important, all the tokens which preceded, the complexity of predicting all the tokens in the sequence of length n is n squared. And apparently it is a problem. It is a problem for the sequences which are more than millions tokens of length. And from my personal experience, there is no LLMs, not Sonnet, and not ChatGPT, which is really capable of working with more than 30K tokens context length, and this is a big problem. So the problem is the slowness in inference. Do you remember what is RNN, LSTM, GRU? Maybe we have some old people here who remember. Now it is almost dead. There are some papers which go out about RNN and GRUs, but it's practically dead. But 6 years ago, 7 years ago, it was very popular before the transformers were invented. And what is the main advantage of RNN? The main advantage of RNN is the fast inference. And why we have this very fast inference? We have this very fast inference because in RNNs, and also in all this generalization of RNNs, which is SSMs and GRUs, and there are many generalizations of it, we compress our memory into a constant amount of vectors. It can be one vector, it can be two vectors, it can be three vectors, but it is predefined a constant amount of vectors, and these vectors just represent our past. And what is our past? Our preceding tokens. So we don't explicitly attend all the tokens which precede the token we are going to predict. We just compress our memory into this one or two or three vectors, and then we just can predict the next token based on this representation. We don't need to explicitly attend all these tokens before it. So theoretically and practically, we have a complexity of O of n, that, when n is a sequence length, and it seems that the problem is kind of solved. But RNN has a very big issue, and this issue just caused them to die, practically to die. And this issue is that the training of RNNs and also GRUs and LSTMs is not parallel. We can't parallelize this training, so we can't train our RNNs on a huge amounts of data and just think about current data set sizes, which can be tens of trillions of tokens, and you just can't train them in a parallel way, like you train the transformers. And why you can't train it in a parallel way? Because of this memory representation. And we will talk about. By the way, it is a mathematical fact. We just can't do it. And the reason is that they need the representation of the previous token in order to predict the next token, and then we need the representation of the token of the tokens before it, and we can't parallelize it. Wow, it is a difficult word to say. And actually, it is the reason that RNN died, and we don't see it almost anymore. Okay, so let's summarize the stuff we had until now. So we have transformers, which is very fast in training. By the way, why transformers are very fast in training? Transformers are very fast in training because we can predict all the tokens simultaneously. We have some masked tokens. Yeah, for example, we have some 50% of the tokens which are masked, and we want to predict it during training. And then we can predict them simultaneously in the same manner, because each token attend explicitly all the tokens. Okay, and this is not the situation in the RNN, and that's why RNN training is not parallelizable. So in transformers, we have a very fast training, which actually enabled training our LLMs on a huge amounts of the data, which are tens of trillions of tokens. And for RNNs, the training is very slow because we can't parallelize it, but the inference is very fast. So we have some, I can call it no free lunch. Okay, you can just you can enjoy of one of the two words, and but the question is it so? Maybe we can think about some memory representation which will allow parallelizable training, and also will have very fast inference. Okay, and SSMs, state space models are all about this. How we construct an architecture which we can train in a parallelized manner, and also in this inference is very fast. Okay, and for the first time, these SSMs were introduced in this paper, which is not a very well-known paper, and this paper dates back into 2019, and it is called some frightening name, memory modeling, Legendre memory unit. Legendre was a mathematician who lived, I don't remember when, but was quite famous mathematician. It has polynomis called on his name and had some quite enormous contribution in math. And what is the main idea? Okay, and all the stuff of SSMs is based on solely this idea. The idea is quite simple. It is not very complicated. And the idea, what we are trying to do, we are trying to build some memory representation of our sequence. Okay, and our sequences, which you can think of, are discrete sequences, but it doesn't have be this way. We can think about some continuous function, which we want to remember, which we want to build some representation of the past values of it. For example, we have some function, u of t, and we want to build some representation of all the values until some point t. And we will build it by the linear combination of some orthogonal polynomials, which is called m of t. And m of t, you can understand that m of t means memory here. It is not. I call it m of t on purpose. And then we just want to build this representation, which just remembers all of the past values of the function u of t. So from the discrete problems, which we have in our LLMs, in a computer vision and stuff like that, we are just generalize it into the continuous domain. And here, m of t is just is a memory representation we are looking for, and there is a mathematical fact. And this mathematical fact is quite known. Is quite known, and the polynomis, you know, we have here an orthogonal polynomis with the coefficients m of t, and these polynomis, you can tell that these polynomis are Legendre polynomis, and from here comes the name of this paper. And so the idea here is to take some polynomials, which are predefined polynomials. By the way, I think I have it on the next slide. Here you have shifted the Legendre polynomials of some order d equal to 12, and here what we're actually doing, we have some input signals, and we want to build some representations which actually remembers each signal. By the way, as far as t grows, this representation may become less precise, but it is the price we pay for working in a long context. But still, we can try to use this purely mathematical representation in order to build some architecture of neural nets, which is based on space-state models. Okay, so now some a bit tough mathematical stuff. I don't know how many of you remember differential equations. It's no partial differential equations, ordinary differential equations. Okay, and it turns out that for these Legendre polynomials, the memory coefficients of this representation are given by this differential equation. And this differential equation, it describes the propagation of this memory coefficient. So I'll try to summarize what I told before. We are building a memory representation of this function u of t, and this representation, m of t, is given by the differential equation. So we can start from point t equal to 0, and we can build all this representation, okay? because this polynomial, this Legendre polynomial, are well known. We know how to build it. We have some exact mathematical formulas. And there is very important fact about this formula, and this fact, which is crucial, I can tell it is quite crucially important, that A and B are constant matrices, and these matrices don't depend on T. And this is important, and we can see in the next slides why it is very important. Okay, so what I covered up to now is just a continuous representation of some function. Okay, so but we are not very interested in representing continuous function, because almost all the data we have is discrete. So we need somehow to discretize all this stuff and to take these differential equations and to make them discretized. Fortunately, it's quite easy to do, because any of you who remember ordinary differential equations or how we can solve it numerically, all the numerical methods of solving differential equations, which we can't solve exactly, are based on this discretization. You start from some point and then you propagate your solution. And this is exactly what this paper introduced. Okay. By the way, what you can see here is quite similar. If any of you remember what was LSTM and GRU, it may seem you a bit similar to LSTM and GRU. All this connection, and this formula is crucially important. Okay, and why it is very important. And now I can tell you why actually RNN died. Okay, we already know that RNN died because we can't parallelize this training. But why? But why this training can't be parallelized? What is the mathematical reason for that? I told you that there is a mathematical reason for it. And this mathematical reason is a nonlinear transition between the hidden states. And this is the solely reason why we can't parallelize it. Okay? And here, what you can see, by the way, M of index T, it is just a discrete representation of our function, of our continuous function, M of T. Here, we just got rid of this nonlinearity. By the way, you can, for RNNs or for STM and GRU, you can just take a look on this formula and you will understand it very fast. You just have non-linear transition between hidden states of your system. And here we just got rid of it. And now, by the way, the equation introduced in this paper are quite complicated, and I'll try to simplify it a bit. And here we have an input, and our purpose is to predict the next token or build an output. And it is quite simple. At the first stage, we update our hidden state, okay? And this update is linear, and here matrix A doesn't depend on T, but it has not been this way, and we'll talk about it in 5 minutes. And then on the second stage, we are building the representation. They are building our output. Okay, it is very simplistic representation, and all these SSMs, which is a very active area of research now, you have much complicated formulas, but the mathematical idea, all the mathematical idea is in this slide. Okay, you don't. In order to understand how SSM work, you need to understand this slide, and it is plain simple. Okay. Okay, but we have some problems here. And why do we have some problems here? Do you remember all this Legendre stuff and all this mathematical equation? The problem of this mathematical equation is that it supposes that we have some predefined function A, which is defined on one of the previous slides. And unfortunately, this function is not working very good. They tried to train SSMs on some data, and it didn't work very good. So, and there are additional issues with this choice of the matrix A. And by the way, when I told you then the SSM is a very active area of research now, all this research, or almost all this research, is concentrated on how you build this matrix A. Okay, there are papers of 50, 60 pages which are discussing how you build your matrix A in this way or in that way, and why it is good and why it is bad. And I think 70 to 80% of this paper just discussing this matrix A. Okay. But as I already told, we are living in a discretized world, and here is our discretized representation. You have already seen it on one of the previous slides. By the way, when I told you that we can quite easily discretize all these differential equations, this discretization is not in any way unique. I gave you 2 examples of possible discretization. I know at least 2 more discretization methods. Okay, and now we will see why these discretized SSMs actually are an RNN. Okay, and anyone who has seen in his or her life RNN can easily recognize this image, because this is RNN. I can just redraw this image in this way, and this is RNN. But this is RNN with some benefit. And what is this benefit? And this benefit is that the transition between hidden states are linear now. So at least theoretically, we will discuss some issues with that. At least theoretically, we just got rid of one of the main obstacles which prevented using RNN for our current models. Okay? Of course, the life is not very easy, and we're going to discuss it in the next slides, but still, at least theoretically, we have something. Okay. And okay, and now, as I already told you, we can train it as we train our transformers. And how do we train our transformers? Very easily. We mask some tokens, and we're trying to predict these tokens. It depends on the encoder and decoder, but still, the main idea is that we can do it in the parallel fashion. And it happens only because of this linear transition between hidden states. But we have some problem here. And here you see this problem, okay? Can you spot the problem with this simultaneous parallelizable computation? This formula is an exact mathematical formula. And for the input, this formula just describes how you get output y of k for your inputs, okay? And you have many matrices here. And you have many matrices which are raised in some powers, okay? And you can easily tell anybody who remembers the bit stuff which he or she learned in linear algebra, remember that raising matrices in some big power, it's a bit problematic. It has some not so good complexity, okay? So the problem here that at least theoretically, we can parallelize our training, but we need to find some way to multiply these matrices in an efficient way, okay? And as I already told, most of the research on the SSMs, on the architecture which are built upon SSMs right now, is about how you build this matrix A. Okay, and here I'm talking, and here, by the way, this representation is very similar to a convolutional representation. Actually, it is a convolutional representation. It is a convolution which we are familiar with from our convolutional neural nets, which are more or less dead right now, but still. But the issue here that compared to this to CNNs, when we have kernels of size 3 or 5, here we can have a kernel or, or number of sums. We can have it 1 million, we can have it 10 millions. It depends on the context length. So actually, we have some problem here, and we need to tackle it. And here, this is this convolutional presentation. So now this slide, which summarized what I've been discussing before it, you have a continuous representation, okay, which is some mathematical formula, some ordinary differential equation, and we have a recurrent representation, which is easily computable, and we have a convolutional presentation. But remember that for long context, this convolution can be very, very far, very, very long. Okay, so I will skip these slides, not very important. Okay, so now I want to discuss a bit how we can compute these representations, these convolutions in efficient manner. This is our convolution. The most natural way to compute it in a very fast way, just tell, okay, let's make our matrix diagonal, and our life will be very good. All this raising into degree of million will be very simple, but still it turned out that it didn't work. Okay, they tried. They tried to. There are some papers which try to train SSMs with diagonal matrices A, and these attempts were not successful. And as I already told, I'm telling you in the fourth time that this is a very active area of research, and many researchers are trying to find kind of an optimal form of A, which is kind of trainable for some domain or for some given data, and also enables of fast computation. Okay. But as I already told you, then you open the papers about SSM, have very complicated images, complicated peaks. For example, you can see something like that, which is a quite famous paper, which is called S4. And what this paper did, it did something very simple. It just stacked a lot of SSMs, one after another, and built something which is called stacked SSMs, or S4. It didn't end there. You have also S5, which stacked all these multiple SSMs in a bit different fashion. And there are a lot of research on that, and there are many architectures like that. And take into account that these linear equations that we see, we need to maintain only linear transitions between hidden states. So for other stuff, we can push some non-linear functions, non-linear activations, which we so love to push in our neural net architectures. So then I showed you this basis of the SSMs. You can imagine that you can push there some non-linearities. Okay. So we've been talking about SSMs, and one of the first slides I told that the fact that the matrix A is a constant, doesn't depend on T, is very important, and this fact and it impedes the performance of SSMs in some cases. And what does it mean? It means that the transition between states, between hidden states, does not depend on the token itself. So you just multiply your xt minus 1 by some constant matrix A, and you just get h of t, which is a hidden state of the token number t. So you neglect your current token representation. Okay, and it is quite problematic for some tasks, which is selecting copying or induction heads. You can imagine these tasks about, and then maybe many of them. It is a very famous paper, and it was published, I think, in the beginning of the year, which is called Mamba. And Mamba told, okay, so the problem was that this matrix A does not depend on the representation of the current token xt, and let's make it actually dependent of it. And then this way we can enable our architecture to solve a bit more complicated problems, just selective copying and deduction heads, which you saw on the previous slide. And this is actually the main idea of Mamba, making this matrix A context depending. By the way, when I told that then most of the research on SSMs is focused on the building of matrix A, the 30%, the rest of 30%, focused on how do you enable how do you enable efficient computation of all these convolutions. Okay, so many hardware optimization, how do you work with GPU and SRAM and HBM, many quite fascinating stuff. And this paper introduced quite a cool optimization, and they also used some gated MLP. I'm not sure it contributed to the performance of this method of Mamba, but still there is a very important distinction of Mamba from the other SSMs. Okay, so what do we have? We have these transformers, which are fast in training and slow in inference, and RNN is vice versa. And in Mamba, we actually have parallelizable training, and also we have very fast inference. But you know, the life is not so simple. It can't be very simple, because you know all this. By the way, the manner that matrix A is made dependent of representation of xt is very simple. It is a very simple representation without any nonlinearity, and all these matrices B and C, all these representation are also quite basic. So we have fast training, and we have efficient inference, but still we don't have the same expressiveness as we have for transformers. So there is a gap. There is still a gap in even for the most advanced SSMs. There is still a gap. We can't use our SSMs in our large language model, for example. Okay, and but where we can use the SSMs, there are some domains which are a good fit for SSMs, and all these domains have one thing in common, and this thing is a very long context. Okay, so okay, we just degrade an expressiveness of our neural architecture, but still we have some gain. Okay, we have fast training, and we have very fast and efficient inference. So we can't use it. We can use it for audio processing. We can use it for genomics. We can use it for video processing, and also for small and very efficient LLMs. Unfortunately, I didn't see many research about small and efficient LLMs. There were 2 or 3 papers, maybe a bit more, but still it is quite promising direction. And one more thing, it is not in this presentation, but there are some attempts to combine these SSMs, these transformers. There is quite famous architecture which is called Mamba, which was introduced by A21 Labs, which is a quite famous Israeli company which is doing NLP of Amnon Shashua. And it just put one transformers block combined with 8 or 16 blocks of SSM. So you somehow get your stuff from 2 worlds. You have some transformers which explicitly attends all the tokens, but still your computation is kind of fast because you have much less transformers base layered, and your computation is quite fast. And you know, it is a very interesting development. And by the way, there are more papers about it. I think A21 Labs was the first company which did it. There are some papers about it. And so what did we learn today? transformers and RNNs, pros and cons, and training and inference, what is state space models, and SSMs, which is between RNN and transformers, and we started at least from memory modeling with continuous function, and we discussed very briefly an evolution of SSM models, and then domain, which can be tackled at least potentially with SSMs, and maybe there are some which I forgot. Okay, and then I told you that this SSM research is very active. You can see here in this slide. There is just one repo, one of the repos which is dedicated solely to stuff which is related to SSMs. And I just, it is about what, and you can just see how many stuff that are here. And there is not all the stuff in this repo. There are much more in this repo. I think there are more than 200 papers about SSMs in this repo, most of them from the last 2 years. So this area research is very active. And it is the end. Thank you very much.
I have 2 questions. The first one may be stupid, the second one I hope no. So my first question is there a specific reason to use like Legendre polynomial? Because in the market there is lots of orthogonal polynomial bases.
Yeah.
And the second one is it's very interesting the presentation, but I still missed why it's so complicated to exponent the matrix, and especially why it's not possible to rewrite the dynamic equation in the diagonal of A. Transforming all the bases.
Okay.
Can you please repeat the question, please?
The first question was about using of different polynomials, and we have a lot of polynomials. And the answer to this question is very simple. Except for Legendre polynomials, there are papers which used Laguerre polynomials and Chebyshev polynomials. And I think the stuff which is close to Legendre polynomials work the best. And the second question was, and I can say that I don't have an exact answer on this question because we're in deep learning. Okay, we don't prove our stuff mathematically. We just try, and if it works, it works, and if it doesn't work, it doesn't work. And but the question was, why can't we convert this exact mathematical form into some dynamical system? By the way, this SSM representation also appears in the dynamical system and is actually a dynamical system. Okay, and why it is not working with diagonal matrices? The problem with diagonal matrices is that it is not representative enough. Okay, so there are many tasks. Even if you are doing it in a Mamba style, if you are doing these matrices A, B, of C, depending on xt, still it is not representative enough. Why? I don't know. I don't think maybe somebody who is doing research on these topics knows, but I don't have any idea. It just didn't work. And by the way, today's research, they are not using the matrices from Legendre polynomials or Chebyshev or Laguerre polynomials. We are trying to engineer these matrices by themselves. Matrices which are some very complicated multiplication of blocked matrices, and then each block is diagonizable. Well, it's tough. It's a tough word to say, but unfortunately, as far as I can tell, I don't know the answer for it. You have to have some reason for all this paper. You have 200 of papers, and people are trying. And the stuff work, and I think mostly it doesn't work. But maybe sometimes, some researcher will give an answer. By the way, there are some theoretical papers about SSMs. I admit that I read only one of them, and it was about a different question, not question you asked.
Thank you.
We are in deep learning. All in all, we are in deep learning, Yeah.
How can you be sure that this formalism is expressive enough with the linearity assumption and everything, expressive enough to solve like language tasks? And are there some like example like results or benchmarks like comparisons to LLMs, for example, regardless of the performance of the training?
Yeah. Okay. I can address this question. And for LLMs, there are some papers, and for LLMs of some modest size, up to 1B, maybe 2B, SSMs may have comparable performance, not the best, but comparable performance to the best of LLMs of which sizes. But I have to say that from my experience, most of LLMs of such sizes are really bad, and in my company we are doing a massive fine-tuning of any of these small LLM. So being in part of these models for SSM, it is not a very big deal. And the answer is the same. We're in deep learning, but we're trying to get our stuff work. But for example, for audio, and think about audio. In audio, you have your signal, and you divide it on some intervals, and you do some Fourier transform or some cosine transform in each of these intervals. So you may have millions of samples. But if you lose 10% of these samples, I think it won't affect your prediction. In language, it is not this way. So SSMs are tailored to the tasks which actually, in fact, have a very long context, but the importance of each token of this context is not very high. So I think anyone who understands it who understands this simple fact won't try to build a very large LLM based only on SSMs, but use it for genomics maybe, or for audio, or for very long videos. You don't need all the frames in your videos. Okay. By the way, there is generalization of SSMs also for videos and for image generation. So there are a lot of generalization in any domain: audio, video, whatever you want. But still, this gap in expressiveness exists. Okay. It is not erased, and my personal opinion, it's not going to be erased, okay? Because you have a fundamental limitation here. This linear transition between your hidden states is a limitation, okay? You can stack your SSMs, you can build thousands of layers of your SSMs, but still, this is a limitation.
I wonder what's your opinion about RWKV? So supposed to be
it was supposed to be, but it almost disappeared now. Let's say that the last time I heard about RWKV was many months ago, and when you are looking today on the LLM's papers, you see very good performance on many benchmarks, but most of the models introduced in this paper just disappear. Okay, there are quite a few models which actually survive and accompany us in our research and our work. And for RWKV, it is a bit different. I don't want to come into the mathematical stuff. It is a type of linear transformer, but still it has some linear attention. It is a bit different from SSMs. So I'm not sure that they're equivalent from the mathematical point of view. I need to check it. Maybe it is, but I'm not sure. But anyway, just as there are a very famous paper called XLSTM, which of this German scientist, and there are a lot of buzz about this paper. It was in June. Did anyone hear this paper now? It's dead. Okay, it was a lot of buzz, and also was a lot of buzz about RWKV, but the fact is that there are almost no people. There are almost no researchers who use this model. So, the reality check. Yeah. Oh.
It's just about practice. Did you try to implement that, and what result you achieved?
Actually, I try to implement it. I'm not specializing in the audio domain, but I try to implement it for some audio task for detection of voices of person in some conversation. And I have to admit that I failed totally. But I think the reason was that I didn't have enough time to invest into training. You know, I built I took some repo, you know, modified it with the help of Sonnet, Claude LLM, and tried to play with it, and it didn't work. I wasn't able to train it, but you know, I invested in it maybe 3 hours in total. It's not very serious.
And it's related to your startup?
No, it's not related to my startup. We are doing cyber. We are not doing audio. At least not at this stage. Yeah.
Thank you for the great lecture. It's very interesting.
Thank you. Thank you very much.